Recording. Yeah. Okay. So welcome to the class. So I'm going to start with this question that I just got, and let me just repeat the question, and we can start. Okay. The question was, in developing the exploit, we sort of had a discussion on what the payload should be and how to engineer the payload, but we did not discuss what the return address should be overwritten with. Okay, so let's take a look at this picture, which is I just modified it from the picture that was already there previously in the slides. So what you see over here is that this buffer is the one that's being filled with the attacker's input. Okay, so the attacker can inject all sorts of things into this buffer, of course, part of which will be the payload, right? The payload is the actual exploit code that spawns the shell. So what is the return address going to be overwritten with? Well, you want to overwrite, the return address with the with this byte over here. If you can see my arrow, you want to overwrite it with the first address where you have started writing the attack code, the payload. And so what happens is that when this function returns, this return address will then point to this location, and then the payload will start executing. Okay, so there are a couple of complications. Okay, by the way, so what I've shown here is that this payload over here, is actually it's being written on top of the return address. That's not entirely right. So maybe the payload comes somewhere over here. Okay, above the return address, or maybe the payload fits entirely over here, right, under the return address. Either one of the case, right? The payload cannot actually overwrite the return address. In the sense that the return address should actually point to the location of the payload, and the code cannot override the return address, whatever it is, right? So the code is over here. Let's say the return address will point to this first location right here. If you see where my arrow is currently pointing, that's the address that the return address has got to be overwritten with. Now, the question is, right, I mean, some of you mentioned, right, I mean, there is a trial and error process in trying to figure out where the beginning of this payload is, and that is true, right? The trial and error process will work. For example, if you don't have this particular defense that I'm going to be talking about later in this class called address space randomization, address space layout randomization, or ASLR, if that is disabled, and it's kind of turned on by default in most modern operating systems, you can disable it. I will show you how to do that. We will look at the virtual machine. But if you disable that, you will find that every time you start the program, in fact, the buffers are located in the same location. Okay, so the attacker is going to be able to figure it out at home, and assuming that all machines run the same kind of program with the ASLR turned off, the same exploit should in principle work. Okay, that's one. And the second thing that I wanted to say was, even if there is some uncertainty in the beginning of exactly where this attack starts, which is where my mouse is currently pointing, you don't have to make the return address point exactly to that location. Okay, generally speaking, that is very hard. So what happens is that attackers they insert what is called a no-op sled. Let me also show you what that is. So you don't know exactly where the payload is going to start within the buffer. There is some uncertainty about that. So what attackers generally end up doing is that they do not start the exploit code. So in front of the exploit code, they add some no-op instructions. The no-op instruction is instruction code 90. It's just one byte. And what happens is that they put a whole bunch of no-op bytes right at the very beginning. So this stuff shown in green, for example, is a bunch of no-ops that is inserted before the payload. Okay, so this is called a no-op sled. So let me just write it down over here. It's called a no-op sled, and the reason that they insert this sled is because the return address now does not have to point precisely to the first instruction of the payload, but rather it can point anywhere inside this no-op sled. Okay, so you can account for a little bit of uncertainty. And the advantage of doing this is that you can point to any byte over here, and the attack will still work, because what it will do is that it will return to the no ops let. It will execute a whole bunch of no ops and then start executing the payload. Okay, so you can make your attack work even if there is some uncertainty about exactly where the payload starts. In fact, you will find this no ops let in one of the homework levels. I forget exactly which, 4 or 5 or something like that.
Nitro level, yes. Sir.
Nitro level, right? So you
Yeah.
have to actually create a no ops let in order to get the payload to work properly. Okay, so I forgot who answered the question, but does this answer your question of exactly how you should override the return address?
Yes, sir, that was the question. If there is only trial and error method, or we can, is there something else?
So it could be deterministic if there is some uncertainty. Then you insert this no ops let. So the no ops let is a fairly robust and resilient mechanism to get rid of this kind of uncertainty. So again, this is part of the engineering of the payload. Okay, there was
Yes,
one
sir,
more
thank you.
question. Sorry, go ahead.
Sir, yes, sir, thank you, sir.
Yeah. Okay. So there was one more question about stack canaries, but I will take that now. So because I will stop where I started, I will start off with this runtime checking of canaries. Okay. So I left you with a puzzle, right? So I told you about this notion of the canary being saved on the stack and the value of the canary being saved in another page. And the fact that a buffer overflow will do a linear overwrite of this buffer, overwrite the canary, and then overwrite the return address. So if there is a mismatch of the canary with whatever is saved in that other page, you know that there is a problem. And I'd asked you to think about ways in which this could potentially be defeated. And there was some discussion in the Teams group. Those of you that have not had a chance to check out the chat window, please go and check out. There was a good discussion. Some approaches were discussed, good approaches, but they don't entirely work. It doesn't matter, right? I mean, that's how you should think. But I had left you guys with this thought exercise. I mean, how do you think you can break this defense? Any thoughts? Let me see. Any question? Please raise your hand and try to give the answer. Yes, somebody tried to raise the hand. Yeah, Shashank, please go ahead.
Sir, I do not know if there is something to break canaries, but I know a case where canaries won't be useful. Like,
please go ahead. Yes.
Yeah, in case of a particular feature is function pointers. So if we have a function pointer somewhere in the function which has the buffer, and we are somehow able to overflow the buffer and strategically replace the value of the function pointer with some other code.
Excellent point. Okay, and it's coming up in the very next slide. Okay, so Shashank's point was spot on. We will discuss that, right? That's one of the ways in which stack canaries is not useful. Shashank, please continue. You had something more to say?
No, sir. I could not see anything else like how to defeat canaries or sort of. Yeah.
No, but that itself is an excellent break. Okay, so so let us sort of look at that. So because Shashank mentioned this, let me just go out to the very next slide where I explain this what Shashank just mentioned. So among the things that are stored on the stack frame are local variables, right? And local variables need not just be things like integers and character buffers. They can be all kinds of variables. For example, one of the things that you can store on your stack frame are function pointers, right? So function pointers are also local variables. Now, many of you must have studied function pointers at least, when you got introduced to C. And when the first time you see something like function pointers, they might actually look like exotic objects, right? The fact that you can take the address of a function. But in fact, they're not exotic objects at all. They are used all over the place. So for example, C++, right, the way you implement things like inheritance and, where you have classes and subclasses and so on, the fact that one method can override the other, all of that is actually implemented using function pointers. In fact, in C++, it is called vtables or virtual tables, where you try to figure out which is the function that you must call when a particular function name is invoked. Because based upon whichever is the subclass or the that's currently instantiated, that's the function that should be invoked. So it's not clear at all when you look at the source code which function should be invoked, and it only becomes clear at runtime. So function pointers are used extensively in low-level languages, including C. And so one of the things, if you can store on the stack frame is a function pointer, then think about a case where your array just after your buffer that stores. Let me just go back to the slide. Just after this buffer that stores this attacker crafted input, supposing you have a function pointer that stored this location that I'm pointing to by the mouse, then essentially what happens is that when you override the buffer, you can also override the function pointer. Okay, you can override now the function pointer with an address of any location in memory. Okay, it need not even be the stack. Maybe you have like another buffer in the heap where you manage to do an overflow and write some code. Or you don't even have to do an overflow. You just wrote something into the heap that's actually executable code. And right here, using a stack buffer overflow, you override the function pointer with the address of the payload that's sitting in the heap. Now imagine what happens, when this function returns. So the exploit doesn't get triggered when this function returns because you might not override the return address, and that's okay. But what happens is that you overrode that function pointer. When you override a function pointer, that function pointer is probably stored in some struct in memory. Why do you create function pointers? Well, at some point in time, you're going to dereference those function pointers and invoke the function. Okay, so when that function is invoked, what is actually going to be invoked is not the function pointer that you originally intended, but rather the address that is written by the attacker contains the function. And that is where control is going to go. And because the attacker has injected code at that location, that code will now start executing. So the exploit will take effect whenever that function pointer is dereferenced and that function is invoked. Okay, so that is a very important problem. What this slide over here shows is that, in fact, this trick of using stack canaries can be extended from the basic mechanism that I showed you to also protect stack-based function pointers. And this was actually implemented in a compiler that was released by IBM around 15 years ago, soon after the StackGuard paper. But the idea is that you identify stack function pointers wherever function pointers are stored on the stack, and then you store them over here right above the canary, so that the canary not just protects return addresses but also protects stack function pointers. Okay. More importantly, a concept that I want to describe over here is that whenever we think about the stack, right, the stack is actually storing data, right? It's storing data that's corresponds to local variables. It's storing data that the function needs for its execution. So all of the stuff in the stack is also is just data, including the value of EBP and return address, right? In some sense, these are just addresses and these are just data. These are values that are stored in registers. These are not actual code. But the point over here is that these pieces of data are critical to in controlling the control flow of the program. Okay, so in fact, what I will call them, I will use a special term to reference this kind of data, and these are going to be called control data. Okay, these are control data of the program because these data values actually affect the control of the program. Okay, so the return address is an example of control data. Function pointers are another example of control data, and you can also have other kinds of variables which are not really addresses that are control data. So for example, imagine a program, and I'm going to use this slide over here just as an example to write some code. Imagine you have a program like this, if variable, then the true case, and else false case. Okay, so what this is essentially saying is that based upon the truth of this variable, let's just say variable equal to 0, right? Based upon the truth of this predicate, variable equal to 0, you're either going to follow the true case or the false case. Okay, and this programming pattern is pretty common in some applications where they check whether, let's say, you're authenticated as root or you're authenticated as a non-root user, wherein you might check, let's say, the user ID actually matches 0 or not 0. Okay, so in this particular case, what happens is that if you were to change this user ID value, which is an integer, it's not really an address, and you had the ability to override this user ID, which might be, let's say, a local variable that's stored somewhere here on the stack, then using the change of this variable itself, you can control where the program goes, the true case or the false case. Okay. So what I should note over here is that it's probably not as dangerous an attack as code injection, this particular attack, because you're just using the program's code against itself, but it's still dangerous nevertheless. In any case, right, these control data values that, for example, return address, maybe even things like this user ID and function pointers, they are critical, and it's important to protect these kinds of control data values that are stored on the stack. So one way to store them and protect them using stack canaries is this particular technique where you put the canary to protect not just the return address but also the save frame pointer, as well as any other function pointers and so on. Okay, so that is one trick whereby you can use the canary to protect the frame pointer as well. Let me quickly ask the class. You can see my mouse movements, right? Because this was a problem in the last class.
Yes, sir, it is visible.
Okay, good. Okay, all right. So, Shashank's point over here, we have sort of addressed. This is one problem, and you can still protect them with canaries. But this is, this is not the only way that you can defeat stack canaries. I mean, for example, if stack canaries do not protect the function pointer, there are also other more dangerous ways by which the canary-based defense don't work. So I will give you two examples later on in this class, time permitting, or I will talk about them early in the next class. In fact, the kinds of exploits, I've only spoken about the simplest form of memory error exploits, which is stack-based buffer overflows, where you do a linear overwrite of the buffer and then overwrite the return address. Okay, that's just the simplest way of doing memory error exploits. If you go and read the or follow modern exploits, this is not the way that modern exploits work. In fact, they're much more sophisticated. And I'll give you a hint of how these things work. But essentially, the most dangerous form of attack that one can think about, and that is possible, and I will give you some hints as to how this is possible, is a memory error exploit where an attacker is able to specify an arbitrary address in memory to overwrite, and also provide an arbitrary value to overwrite that memory location with. Okay, so in other words, an exploit where the attacker can say, look, here is a particular address in memory, I want to overwrite it. So here is the address I want to overwrite. Let us call that address A, and I'm going to give you a value V, and I want you to write this value V into that address. Okay, that is possible. So there are methods by which you can now specify an arbitrary address in memory and an arbitrary value to override that location with, and that is, it's just going to do that one particular modification and nothing else. Okay, so it is by no means a prerequisite to do a linear overwrite, for example, over here of the stack canary and the return address. There are exploit techniques possible where you can directly specify the return address that you want to modify and provide the value that you want to modify it with, and the attack will just work. I will give you two examples. I will just mention them over here. So they are heap-based exploits. I'll give you a hint as to how they work. These are extremely sophisticated exploits. I'm not the expert here. I'm not going to try to pretend to explain how they work. In fact, there is an expert right here in this department that knows the A to Z of heap-based exploits, and that's Ajinkya Rajput, who is a PhD student in Professor Gopinath's lab. So you can always ping him if you want to know about heap-based exploits. He is really looking deeply at this problem. And the second exploit technique that I'm going to talk about is an exploit technique called format string exploits. These used to be extremely dangerous in the mid 2000s. Right now, their prevalence has reduced. Nevertheless, I will show you that I will show you what is possible. Okay, I will show you that using format string exploits, you can just specify an arbitrary address and an arbitrary value and just override that without overriding anything else. Okay, so stack canaries, while they are nice to have, while they are widely deployed, and I have put a pointer to a GCC document that explains how stack canaries are implemented in GCC, they're not a perfect defense. But that doesn't matter, right? I mean, the fact that it's not a perfect defense does not mean that the defense is entirely useless. Security always works by creating layered defenses, right? There are multiple sort of obstacle courses that you set for the attacker, and you want to set as many obstacle courses as possible. So it's clearly useful to have stack canaries. They do have an unwanted side effect, and the unwanted side effect is that of performance overhead. And the reason is because you're doing extra work every time there is a function call and a function return. You can sort of calculate what this extra work is, right? It is this work of doing the comparison, and more importantly, it is this work of storing this stack canary in another page. And if you really want this mechanism to be robust, you want to write protect that page. And so that involves a system call. So it's going to add overhead to function calls and returns. Okay. So I don't know what the latest statistics are. I used to have a number on these slides, but I've removed them because it's not really the latest number. There was, an indication that it sort of, reduces performance by around 8%. That's a pretty bad number, especially if you have a performance critical server. But I don't know what the numbers in GCC are, and you can always run a program and then figure it out with stack protector and no stack protector. It depends a lot on whether the program is IO bound or CPU bound. But that is something that you should be aware of if you're using stack canaries. Okay, and GCC is actually pretty flexible. You can ask to protect specific functions, or you can protect the whole program. So that flexibility is there. Okay, let's stack canaries. There's much more that you can do, not just stack canaries. You can also use safe libraries. In fact, the use of things like stir copy, getters, and so on are the main reason why you have buffer overflows. Not the only reason. I mean, you can easily do pointer arithmetic, raw pointers, play with them, and have buffer overflows, but this is one common way. So safe libraries are one way to avoid buffer overflows. Use stir n copy or stir l copy. But that is, of course, if you have access to source code, or you have the ability to relink your program with a safe library. But if not, what do you do? Well, here is one way to implement a safe library, right? Which is that the problem with something like stir copy is that where you just specify the destination of the source, but you don't specify how many bytes of this source buffer you want to copy into the destination buffer. So ideally, you should do that, and something like stir n copy or stir l copy allow you to specify the number of bytes. So you specify the number of bytes equal to the amount of space that you have allocated on the stack. But if not, what do you do? Well, one safe way to do it, assuming you don't have something like function pointer saved on the stack, is that you can assume that the location of the saved frame pointer on the stack is the end of that stack frame, and you can give a conservative estimate that the frame pointer location, the saved frame pointer location, which is EBP, which is available to you in assembly code, minus the actual pointer that corresponds to this destination, that must be greater than the stir length of SRC. So in other words, you should not write more into this destination buffer than this frame pointer buffer. So internally in assembly code, you can sort of inject these instructions to perform this check. It's a very loose kind of check, because you would overwrite other local variables on the stack. And as you saw in that example that I showed you, this particular example, if your user ID equal to 0, and that user ID is saved on the stack somewhere, it will not really protect against that. But hey, at least it's going to protect your return address. So it's a layer of defense if you want to use these kind of safe libraries. And when would you do this? I mean, you would probably do this when you don't have access to the source code, right? If you don't have access to the source code, all you have is the ability to relink against another library, or probably modify assembly code using binary rewriting techniques. This is a technique that you can potentially use to maybe save the return address. Again, it's not a perfect difference. Okay, so that's one solution, and I kind of mentioned it as a possible option. And one of the things that you will see over and over is that, why are we discussing so many defenses? The reason we are discussing so many defenses, in fact, we'll be discussing 4 or 5 defenses, is because each one of these defenses has a different sort of assumption, right? You assume whether you can assume that you have source code. In other cases, you can assume that you don't have source code. You can assume that the binary is instrumented, or there is debug information available in the binary. In which case, it's kind of easier to rewrite the binary, or you can assume that there is no debug information in the binary. you can assume that you don't have all of the code that will execute, that some of the code that will execute will come at runtime and get dynamically linked. And you can also ask questions about whether that code is modifiable or not. You might overwrite your local binary, but you might not be able to overwrite a library that you link with at runtime. So these are all various points in the design space, right? And what we will talk about are various design options, various defenses that cover portions of this design space. Not every solution is going to work in all settings. Some solutions work better than the other in some settings, but nevertheless, we'll explore this design space and try to understand the trade-offs of various solutions. Some require access to source code, some impose higher performance penalties than the others. But this exact sort of analysis is what you would use on the field when you find that you're stuck with a piece of legacy software that you're now supposed to go and try to fix, because maybe there is a buffer overflow that's been reported over there. You can't throw away the library, or you can't throw away the piece of legacy code and start from scratch. What do? You need some way to move forward, right? What are the designs that you can consider? And that's what we'll be looking at probably over the next 4 or 5 lectures. Various points of the design space. What is the strength of these solutions and so on, and we'll compare the strength of these solutions. Okay, so let us start with the first of these defenses. I spoke about this in the last class, but I will repeat it because what we are going to talk about over as the very first thing is a modern attack technique, the return-oriented attack technique that defeats this particular defense, right? And we spoke about this non-executable stack and its more general variant called W XOR X, where the idea is that you mark pages in the program's virtual address space. You mark them as being writable or executable, but not both. So if a page has been written to in the past, it means that it contains data and that it should not actually be executable. And if you have executed a page, that means it contains code that you should never be able to inject code into this page at runtime. Okay, so the W XOR X is basically a policy that you would use. The mechanism, of course, over here, and this goes back to the first lecture of policy versus mechanism. The core mechanism that you're using over here is the fact that these bits, these permission bits, exist in the page table that allow you to specify whether a page is writable or executable or whatnot. And the policy that you're using within the operating system over here is the W XOR X policy, where you decide whether a page should have write permissions or execute permissions, but of course not both simultaneously. Okay, so that's the defense, and that prevents a large class of exploits, including the stack-based buffer overflow exploits that I spoke about, because as you can see in this particular example that we spoke about, the payload, which is the actual code that the attacker needs to execute, is injected onto the stack, and because you wrote into this page this particular payload, this page that contains this payload will not have execute permissions according to the W XOR X policy. Execute this payload, the minute you try to execute it, the hardware will throw a fault, and you can prevent the exploit that way, right? So for the longest time, this was thought to be a safe defense, and that people thought that we had nailed the problem. But of course, I spoke about the last class where this return to libc exploits showed that W XOR X was not a perfect defense. The reason it's not a perfect defense is because you can put the program's code to use against itself. And I gave you one example, right? The example that I gave was this example of the system library call, where you can specify an argument, which is a string. So this is just a piece of data that you insert to the program's address space. And if you can overwrite the return address to point to system and arrange your stack so that the string exec bash, the pointer to it, is passed as an argument to system, lo and behold, you get a root shell. A shell with the privileges of that program. Okay, so this is a return to libc exploit because it's returning control back to libc, which is loaded into the program's address space, and you're able to sort of do this bad thing without ever injecting code into the stack or any other location where data is supposed to reside in the program's address space. Okay, so for the longest time, this was thought to be a rather exotic attack that it's really hard to implement. But hey, at least it showed a proof of concept that W XOR X is not the be all and end all of all defenses. Okay, this is until return-oriented programming came along, and this was in 2007. 13 years ago at this point, and just 2 years ago it won the Test of Time award at the conference where it was presented. So 10 years down the line, they sort of looked at the most influential papers that have really charted the course of the field. And this paper was one of these Test of Time award winners. So it's a really good paper. It's sort of it's out of the box thinking taken to its extreme, and its creativity taken to its extreme. So let's sort of understand what this attack technique is and how it works. Okay, so more generally, what this paper introduced, or this return-oriented programming introduced, is a paradigm. It's a paradigm shift in how buffer overflows work, in the sense that it introduced a new kind of attacks called code reuse attacks. Okay, so what is a code reuse attack? A code reuse attack is one where you take the code of the program itself and put it to use against the program itself. Okay, so you're going to look for that. This is return to Libc is one specific instantiation of code reuse, because you're taking the system, the code of the system library call, and putting it to use against the program itself. Okay, but we'll see that this is just one instance of this code reuse attack. The return-oriented programming methodology gives us a very generic and very powerful way of putting the arbitrary pieces of code in the program to use against the program itself. Okay, so we will now look at return-oriented, and it has fundamentally caused us to rethink OS level defenses against buffer overflow attacks. It shows that this notion of code reuse is a much more powerful attack mechanism than previously imagined. Okay, so let's look at return-oriented programming, and actually let me start you off with the key intuition behind return-oriented programming. Okay, so the intuition here is, it goes back to these ransom notes, probably that you might have encountered maybe in some fantasy novels or something. Okay, so if you look at this ransom note over here, right? It says, "Give us the stamps and nobody gets hurt." X, signed X. So what is unique about this ransom note, right? So the point here is that maybe somebody has done something bad, and in order to, maybe they've stolen something, and in order to return it, they want some ransom. So they don't want to give away their signatures. So what they did was that they took these cuttings from magazines and then they pasted them together to lay out this message. Okay, give us the stamps and nobody gets hurt. And these, each one of these alphabets over here was probably pulled from different magazine or different portions of the same newspaper, but they have essentially pasted together these things to make a meaningful exploit string, or a meaningful string, right? They've taken this GIV from various portions of a magazine, stuck them together, and now it reads like a real message. Okay, and that's exactly going to be the idea behind our return-oriented programming. What we will do, and I will give you the sort of the ending. Of course, the key thing is going to be to see how to realize it. What we're going to see is that, supposing you want to, let's say, spawn a shell. Okay, so in order to do that, we went over the payload engineering in the last class. How to go about creating the attack string. Okay, that you will still have to do. You will still have to sort of understand exactly what is it, the exploit code that you want to write. But instead of just taking that code and injecting it in the program's address space, you're actually going to try to find pieces in the program's own code. You're going to try to see whether the exploit code that you wrote, pieces of that, whether the instructions of that exploit code already exist in the program's address space. And why not, right? I mean, if you go and look at our attack over here, let me just pull up the slides. If you go look at our attack over here, where did we come up with the attack? Here it is, right? Okay, what are the things over here? I mean, if you look at each individual instruction, none of these looks like an exploit. Okay, here is a move well instruction with an ESI. Here's an array offset that you fill. There's an ESI register. Nothing, if I look at this instruction over here in isolation, nothing here suggests that it's an exploit string. In fact, this looks like a perfectly legitimate instruction that I could find somewhere in the program's address space, maybe in its own code, right? So that's the key idea behind return-oriented programming. Can I try to find each one of these individual instructions or groups of instructions in the program's address space and try to string them together, right? They need not exist as a contiguous location in the program. Go try to find maybe, this instruction over here exists at one location, this instruction exists in another location, maybe these three exist as one chunk somewhere else and so on. I just want to string them together, okay? That's the idea behind return-oriented programming. I want to find these instruction sequences that implement an exploit and string them together. Okay, so there are two parts to this attack. I want to find these instruction sequences that are used to create the attack. No individual instruction is going to be dangerous, but when you string them together, it's going to be dangerous. So I want to find these individual instruction sequences, and there is a very specific name that's used over here, and you'll find that there is a very specific characteristic for these instruction sequences. We're going to be calling these instruction sequences gadgets. Okay, remember this name. They're going to be called gadgets. Okay, we are going to find these gadgets in the program's address space, and we are going to string together the gadgets to accomplish some particular goal. For example, this attack payload that you see in front of you. So this attack payload that you see in front of you is going to be broken down into gadgets that you can find in the program's code. And that's the first step, of course, finding these gadgets. And the second step is going to be to try to figure out how to string them together. Okay, you want to somehow tell the program to execute this gadget first, and then this gadget next, and then this gadget third, and so on. Okay, so those are the two meta steps of this attack. So now let me explain to you how the attack works. Okay, it's too early to ask for questions because I've just given you a high-level overview. But let me now tell you what these gadgets are and how to stitch them together. Okay. Okay. So you can see over here the key ideas that I just explained. You want to find the gadgets in the code existing in the program's address space. So gadgets, as I told you, they are nothing but code snippets that already exist in the program's address space, and you want to stitch them together or string them together. Okay. So what is a gadget? So here is the key definition. Please sort of pay attention to this. A gadget is a short code sequence ending in a ret instruction. This is very, very, very important. It is a short code sequence that's there in the program's address space, and it's important that it ends in a ret instruction, and we'll see shortly. Okay. So the reason that it's going to end in a ret instruction is because how we're going to put these gadgets to use in a really brilliant way to sort of create this stitching. You're going to simulate the stitching using the program's call stack. Okay. All right. So what is the significance of the ret instruction and why gadgets and how should stitching proceed? Let me sort of tell you how it works, and then we will see how. Okay. Actually, to show you how it works, let me just go back to the slide. Okay. Okay. So a gadget, as I said, is a code sequence that ends in this ret instruction. Okay. So I'm just going to draw a bunch of gadgets over here. And then, maybe these are all things that are there in the program's code already, right? So remember, these things that I'm showing you here in pink, these are not actually there over here in the stack area. Rather, they are sitting somewhere else in the code segment, right? So each one of these gadgets, and I'm just going to draw three gadgets, G1, G2, and G3. What is the key characteristics of the gadget? Well, it's a bunch of instructions that ends in ret. Okay, so let us just write them over here, and I'm going to also write three things, which is I'm going to write down the addresses where these gadgets are there in the program's address space. Okay, so let me write it down over here. Give me a second, just bear with me. Text box. Okay. Oops. Okay. I don't want that. Sorry about this. This is probably the only way I know how to write stuff interactively in class. I have to figure out a better way to do it. Okay. Let me just get rid of this guy. Okay. So here is A1. Okay. Address, it's a hexadecimal address. And maybe our gadget 1 lives at A1. Okay. A1 in the program's address space is where the gadget 1 lives. Okay. Now let me just oops, what is this over here? I don't need that also. Okay, and A2 is where our second gadget lives, and A3 is where our third gadget lives. Okay, so address A1, A2, A3. Now I'm going to actually describe how to find gadgets and what their importance is and so on. But we've got these three gadgets living somewhere in the program's address space at address A1, A2, A3. Here is how, and let us say that my exploit string that I want to create is actually G1 concatenated with G3 concatenated with G2. Okay, so the real exploit string that I want to construct, let us say that the exploit string can be constructed by just concatenating G1 with G3 with G2 in that particular order. Okay, so the key thing over here is that G1 ends with the return instruction, and G2 also ends with the return instruction, and G3 also ends with the return instruction. Okay, that's key. That is the idea behind a gadget. And my exploit string is supposed to be concatenated by this G1, G2, G1, G3, and G2. Okay, so now what does the attacker do, right? I mean, how does he actually go about creating the exploit? So the way that the attacker goes about creating the exploit is like this. He overwrites the return address and with the return address in this way. He writes A1, the next address he would write A2, and the next thing that he would write on the stack is A3. Okay, so in some sense, what he is doing is that think about it like this: he's going to exploit a buffer overflow, but of course, he is now not going to insert any executable code. Rather, what he's doing is that he's filling this exploit buffer with some stuff. Doesn't exactly matter what. But right here, when he gets to the return address, he's going to overwrite the return address with A1. So that is going to exist in this particular location of this buffer. It's going to insert A2 and then A3. Okay. So now let us kind of imagine what happens when this function foo returns. What it's going to do is that when it returns, it's going to actually return to this address A1. Okay. What does that do? Well, it goes over here and starts executing this instruction sequence G1. Okay, it executes the instruction sequence G1. What does G1 end with? It ends with the ret instruction. Okay, what does the ret instruction do? What is the functionality of the ret instruction?
Sir, it jumps to the next address space, like the next address provided, and then it saves the value of EBP on the stack.
No, it doesn't save EBP on the stack. Absolutely not.
Sorry.
Saving EBP on the stack.
Yeah.
Okay.
That is done in the next function. Yeah.
That could be done by the next instruction, need not, right? I mean, that depends on your assembly language sequence. All ret is a very simple instruction. All ret does is that it looks for the top of the stack, takes the return address, changes the instruction pointer to that location, and pops that return address from the stack. That's it. Okay. So G1, so as you can see, this exploit string over here now has overwritten this guy with A1. So it goes and executes the G1 code sequence, following which you have a ret. At which point in time, the processor thinks, hey, I'm done with G1 now. Let me just go and pop the next stuff from the stack. Sorry, not A2. This should be A3 and then this should be A2. My mistake, because that's how I've strung together the sequence. Okay, so it goes to the stack and it pops off the next address. What's the next address? It pops off the next 4 bytes. The next 4 bytes are what? Well, it pops up A3. Okay, A3 is then treated as the next return address. So the instruction pointer is changed to A3. It goes right there, the processor starts executing the instruction sequence G3, which contains the exact sequence of code that the attacker wants to exploit, followed by ret. Okay. Now what does this ret do? Well, it goes and pops A2 from the stack, and then it goes and executes G2 followed by ret. At that point doesn't matter, because at this point we have the attacker has accomplished his goal of executing G1, G3, and G2 in order. And you saw over here how the attack was strung together, right? The gadget G1 executes followed by ret, which forces the processor to go and take the next instruction, the next value from the stack, and that's treated as the next code location. Goes to G3, G3 executes, ended ret, again go and now pop A2 from the stack, execute G2, and then that ends it ret. Okay, few characteristics that I want to point out. Okay, I will again mention this. I've mentioned this in the past, but I will mention it again. G1, G2, and G3 are gadgets. These are pieces of code that already exist in the program's address space. The attacker did not inject them in this buffer over here. Rather, they exist somewhere down below over here in the code segment of the program. Okay, I will tell you about how we search for gadgets. That's an algorithm called Galileo that I will just describe. But the gadgets already exist in the program's address space. Okay. The key contribution of this paper was to show that there are enough gadgets in a realistic program, for example, libc, to make a Turing-complete programming language. Okay, what's a Turing-complete programming language? A Turing-complete programming language. So a Turing machine is universal, right? You can express any program that there is using a Turing machine. So Turing-complete programming language is one that in which you have all the constructs to express any arbitrary program. And so it turns out that you just need a few basic constructs to create a Turing-complete programming language. You need all the arithmetic operators. You need an assignment operator. You need a conditional and if then else. You need the ability to create loops. And in fact, even loops are too much, right? If you have a conditional statement and if then else, and you have a go-to statement, you can create loops. You can simulate loops using if then else and go-to. Right? So if you have all of these constructs, that's enough to construct a Turing-complete programming language. And what this paper, this particular paper that's actually assigned reading for you, showed that in real libraries like libc, there is enough code and so that you can search for enough gadgets that, when combined, can create arbitrary programs. In other words, this collection of gadgets that you can observe, that you can obtain from a real world library like libc or any other library is actually a Turing-complete programming language. Okay, so you're sort of not thinking about a programming language over here in terms of like C or C++, but rather the basic constructs of your programming language over here are these gadgets, and you're just finding innovative ways of stringing them together. Okay, so this code already exists in the program's address space. What did the attacker insert into the or do as part of the buffer overflow exploit? Well, all the attacker did was to overwrite the return address with these addresses of the gadgets A3, A1, A3, and A2 in this particular order. In this example that I just showed you. Okay, so the only thing that the attacker inserted into the program's into the program stack was data, right? He did not inject any code. All he wrote was A1, A3, and A2, and these are all data. Okay, and the code already exists. The programs where the program's code already resides. So there was no new code that was injected into the program's address space. So W XOR X is defeated because this attack will work even if W XOR X is enabled. And the reason is because you did not inject any new code and you played within the constraints of W XOR X and you were able to get your attack to work. Okay, so this is the basic idea behind the attack. I still have to fill in some important pieces. I have to actually tell you how these gadgets, for example, you search for them and key property of these gadgets and so on. But let me just briefly pause over here and take a few questions. Any basic questions that that folks have that I can answer right away? Yes, Shashank.
Sir, I have a question. Like on the first look, these gadgets look like functions to me, like functions which are spilled across the program in the program space of the program. So why are we calling them gadgets? Like
good point. So they are not full functions. In fact, they're just code snippets, right? You're right that they ended ret, right? You're saying that they are functions because they ended ret.
Yes,
but
correct.
in fact, they're not. Sorry.
Yes, sir. That's why I was saying because they are ending in ret.
True. but they're not full functions, right? They are just code snippets that you find in the function. So for example, you might take the 2 instructions just before the return statement and call that a gadget. In fact, we will see something that a key property of gadgets, which is that if you find a gadget in a program, any valid suffix of that gadget is also a gadget, right?
Okay.
Because the only constraint I'm placing over here is that it should end with the ret instruction, which is you will find that it's C3 in x86. So while you are absolutely right that a function is a gadget, any suffix of the instructions in the function is also a gadget. Okay, so it need not be a full function. It can be any arbitrary instruction sequence inside that function ending with a ret. Okay.
So when we say that it can be like as part of the function, so we can only clip from the top, like only clip from the beginning.
At the bottom.
Right,
at the bottom, right? I don't know what you mean by top, but essentially the ret.
Matlab entry of the function.
Exit,
we can only clip it.
No, you cannot. That's no. You're thinking exactly reverse. So you cannot clip it from the entry, right? I mean, you want to start searching backwards from the ret instruction. You take any instruction sequence ending in ret, that's a gadget. Okay.
Sir, I was not talking about searching. When we say that A1, like A1 can point to some from the starting of the function to any place downwards. Like
it need not be in the starting of the function. It can be any gadget that you find with the program's address space. As I said, any suffix, not prefix, suffix of a gadget is a gadget.
Yes,
right?
Sir, I got it. Got it.
Okay.
Thank you.
Okay. Let's see. Some more people had a hand. Ekaj, please go ahead.
So these gadgets are in the text area of the program or in the stack?
Text area, the code part of the program, the text area.
So
that
is not writable. So how we will enter address? How we will?
You are not writing anything. The G1, G2, G3 are already there in the programs. So perhaps I need to. Okay. One second. Let me just bring one slide from the beginning of the program and beginning of the slides and then show you. Okay, which picture shall I bring? Shall I bring this picture? I'll bring this picture over here. In fact, okay. Just give me a second. I will clarify this for you. Where are the slides? Here. Okay. So let me paste it here, and it'll. Okay. So I pasted it here. Okay. So just pay attention to the right hand side. So this stack over here that I'm showing you. Okay. This stack, you can see my mouse. This portion of what I'm showing you over here, it is somewhere within the stack. Okay. This G1, G2, G3, where do they sit? Well, they sit. I'll just show you. They sit somewhere here, right? Maybe G1 is over here. So this is address A1. G1 is sitting over here. G3 may be sitting somewhere else, right? Maybe G3 is sitting over here. Okay, doesn't really matter where. It's somewhere in the program's code, and maybe G2 is sitting over here. So A1, A2, A3 are just addresses, right? They are the addresses. You're not G1, G2, G3 already are there in the program's code. Okay, the stack is over here. What are you writing on the stack? You're just writing A1, A2, A3. A1, A2, A3 are not code. They're addresses. G1, G2, G3 are the ones that actually contain the code. A1, A2, A3 are addresses. They're locations. All you're writing on the stack are A1, A2, A3. Okay, so you're not really injecting any new code. So this portion over here is executable and not writable. And I didn't ask you to write anything over here. I'm just asking you to write over here, which you do anyway. Got it?
Got.
Okay. Okay. So Aditya.
Yeah, sir. So we can find code snippets as gadgets, but what if I want data? If like I want a variable that stores the number 10, or if I want a string that stores /bin/sh.
I will show you all that. It is there in the paper also. You should go read it, of course. I will show you how you can do arbitrary things using gadgets, and you can write arbitrary values into variables. Well, you don't think at the granularity of variables when you're creating an exploit. Rather, you think at the granularity of registers, right? Because after all, when you're creating an exploit, you're not writing a source code program. You're writing an assembly code program. So I will show you how you can write arbitrary values into registers. In fact, that's the only thing that I will show you. And I will also show you how to create if-then-else statements but in a very, very simplistic way. For all the gory details, you have to read the paper. It's actually a very detail-oriented paper, something that, you know, if I sit and explain in the slides, it's probably not going to fly. It'll probably fly over your heads. So you will actually have to sit and read the paper, but I will tell you how to read the paper, okay? In the sense of how to interpret the diagrams in the paper. The rest you will have to work out with paper and pencil yourself in order to understand and make sense of how each one of the constructs is working. Okay, so that is what I'm going to do next. So so just bear with me. Abhishek.
Yes, sir. Sir, if we say that stack, we don't give write permission on the stack and we cannot have any executable code on the stack.
You need write permissions on the stack. Otherwise, how will your program work? You're not giving any permissions on the stack.
If we don't have write permission on the stack, then this attack won't be working.
If you don't have write permissions on the stack, you cannot execute a program. Why would you
write permissions in the sense the executable code? Like I as an attacker cannot put an executable code in the stack.
Yes. So let me just show you over here. Okay, not executable. Okay. So those pages are not executable, not writable. Okay. I'm not sure I understand your question. This stuff over here is not writable. That stuff over there is not executable. You can write over here. You cannot write over here. You cannot execute this. You can execute this.
Oh, okay, I get it.
Right?
And yes, sir. And one more thing, in an attempt to defend the if we want that canary attack should not the defense mechanism canary. If we we talked about the function pointer, that if we have a function pointer at that place, we will go and inject our code. The function pointer is basically pointing at the machine, where the machine code is stored, which is not writable. So how am I supposed to inject my code?
So okay, very good point. I'm sorry I did not clarify this. Right now, we are not going to assume canaries. You can still implement this attack in the presence of canaries, but let me just, because you asked this question, let me just clarify it. This has nothing to do with return-oriented programming for the others that are listening. So let me just copy this stuff over here and go to another slide and explain to you what that particular attack that I was speaking about. Okay, so you asked about function pointers, right? So let us just assume that we have a stack canary based defense, and what you're doing is that you're overwriting a function pointer that is sitting on the stack. So let me just do that over here. Okay, and for a second, let me just get rid of this not writable, not executable, because we are discussing the stack canary based defense. Okay, so here it is, right? So what you said was that there is somewhere on the stack, and that's what this orange box is going to determine. There is a function pointer. Okay, and this function pointer was sitting somewhere over here inside the stack. So I've drawn it much bigger than the stack, but bear with me. Function pointer is sitting somewhere in the stack. What I said was that a buffer overflow will go and overwrite this function pointer. And your question was, hey, this function pointer is actually pointing to some code over here, maybe a function foo that is sitting somewhere inside this code segment. And you just told me that the code segment is not writable. How can I implement the attack? Well, so what I would do is the following, right? I mean, what I would do is that I would inject code within the heap. Okay, so now let me just call it bad. So I would inject whatever exploit code I want within the heap, and then change the function pointer over here to point to this location bad over here. Now, if you did have W XOR X, you are absolutely right. And I sort of made the heap and I applied it to the heap also, then the attack would not work. Right? That is why I'm telling you about defenses in isolation. If you combine them, yeah, then some of the attacks will not work. But I'm telling you exactly, I'm clarifying how I foresaw or how I explained the function pointer attack as working. If you overwrite the function pointer over here, you can actually make it point to code that you injected. And that could be something that sits in the heap. It need not sit in the program machine code area. Okay? Does that clarify what you had in mind?
Yes, sir. Yes, sir. It does.
Okay. So I've not combined defenses yet. And you're absolutely right, right? If I use W XOR X, then yeah, I wrote it over here, cannot be executable. Yeah, that will prevent that defense, absolutely. And that's why, W XOR X was thought of to be such a powerful defense. But as you just now saw, with these gadgets, you can actually find your way around W XOR X also. Okay, so let's go back. More questions. Ekansh has another question.
Yes, sir. Sir, in function pointer, if we know the location of function pointer, then we can also know the location of canary. Or how do we know the location of function pointer in the stack?
How do you know how did you know the location of the buffer in the stack? You use GDB or you use obstup and you sort of figured out the layout of the stack. And, just like, as I said, the function pointer is a local variable. In this particular, supposing the function pointer is a local variable on the stack, you can just go and do an obstup and you know where the buffers are laid out. That's how you also know where a function pointer is located.
So then can we know the location of canary also by this logic?
You know the location of the canary anyway. It is located just before the return address, or the canary's location is not secret. I never told you that the canary's location is secret. The canary is always placed before the return address. The value of the canary is secret, or rather random, right? The location of the canary was never secret anyway. The location of the canary is just before the return address. Does that answer your question?
Sir.
Yeah, you may want to go and look back or hear back that portion. The location of the canary was never secret. It was always known. It's just before the return address. Okay, so I'll take one more question. I see Mahesh's hand is raised. I will take that question and then we will continue with the lecture. Please go ahead.
Sir, yeah, my question is like we are now assuming that there is no canary defense, right? This whatever issue we are talking about.
So look, this is how the science of security proceeds, which is that you show the possibility of a new attack, right? Now, if you were to introduce more defenses, of course, the attack is going to become harder and harder. I'm just showing you how an attack works. And in order to show a proof of concept, I will make it easy for me to show the proof of concept. So I'm not assuming any defenses exist over here except W XOR X. And I'm showing you that W XOR X is bypassable. Now, of course, you can add more defenses, and this brings the sort of principle of layered defense. And, it will make this particular attack harder because A1, A2, A3 are now going to be harder to overwrite with the stack canary in place. But I said that, there are other attack methods by which I can overwrite arbitrary memory locations with arbitrary values. I can use a combination of techniques to bypass the canary-based defense. That will just make my job as an attacker harder. It's not impossible, harder. That's all.
Okay, thank you.
Okay. All right, so let me just continue, okay, and you can, in case we don't have time at the end of the class, you guys can always leave questions on the team chat window and I will answer wherever I can. Okay, so we did some rough work over here. Let's move on to the notion of a gadget. Okay, so what I will do now is I will explain to you the notion of a gadget and I will tell you how gadgets can be used to implement some arbitrary functionality. So somebody asked, how do I overwrite a variable with an arbitrary value? Let me show you that. Okay. And in fact, we will take the attack that I just described and make it slightly more complex because, you're not just address A1, A3, A2 on the stack. You're actually going to be inserting data values also. That will become clear in just a second. Okay, so what is a gadget? Well, a gadget is just any instruction sequence that ends in C3. Okay, in the return instruction. So what is the return instruction? Well, if you were to go and look at the x86 instruction manual, the hexadecimal encoding of the return instruction is C3. Okay, the hexadecimal code C3 stands for return. Now, what this means is that, the way that I search for gadgets in a program is that I can just look for the C3, the pattern C3 in the hexadecimal binary, and then search backwards from there. Okay. So what this particular slide in front of you shows is that the presence of a C3 instruction in binary code does not necessarily mean that that C3 corresponds to a return instruction. Okay, somebody asked me, I think Sashank asked me, does this mean that I must always start at the beginning of the function or the end of the function? And this slide over here shows you that it need not even be the logical end of the function. And this takes me back to a discussion that I had last class about the richness of the x86 instruction set, which is that you can instructions can be expressed multiple ways, and that instructions are actually variable in length. So I will show you one example over here. Let's look at this first instruction sequence over here that you can see in front of you. Did I share my slides? Are my slides visible? Sorry, please.
Yes, sir, they are. Yes,
okay,
sir.
Okay. And my mouse is also visible, right?
Yes, sir, mouse is also
okay, good. Okay, let's look at this instruction sequence. Test 0x0007 EDI set NZB minus 61 EBP. Okay, now don't ask me what this test and set NZB are. I don't know. You can go and check the x86 instruction manual. They are just one of the few thousand instructions available on x86, but the fact is that they exist. Okay, and if you look at the binary code that contains this, well, it is in fact over here. Okay, so the F7 instruction sequence, the hexadecimal encoding stands for test. After that, there is C7, which likely talks about the fact that C7 means that it's the EDI register, and then the values over here are encoded in Indian notation. 0007. Okay, so F7 C70007 is this instruction, and then the 0F9545C3 is the set NZB minus 61 EBP. Okay, so that is what that is. If you were to start reading the instruction sequence, right? So whenever you load instruction sequence into the processor, you also tell the processor where to start reading. You give it the pointer to the first byte of the valid instructions, and it starts reading from there. And the way that the x86 processor sort of interprets this is that it looks at the first instruction, takes the number of bytes that correspond to that first instruction, because the processor knows exactly how many bytes to read text in order to take all the arguments. And then, it reads all of that, puts it in the processor pipeline, execution pipeline, and then starts reading from the next byte onwards. So if you give F7 as the first byte that you want to read over here, then you would interpret this as a test followed by an NZB. Okay. But as I said, the x86 instruction set is so rich that you can start reading from anywhere, and it will likely decode to a proper instruction sequence. So just to give you an example, so let's say we ignore this F7 over here, it starts reading from C7. Okay, if the processor starts reading from C7 and you were to go and look at the x86 manual, what exactly C7 corresponds to, it will correspond to the move well instruction. Okay, and C7070000F essentially corresponds to the instruction to the instruction move well 0xF00000 EDI. As you can see, the fact that something is EDI, you can see that it is the 07 over here. So C7 is the move well instruction, and this next 5 bytes over here essentially tell that it's move well and these particular 2 values. Okay, but that just takes care of the next 5 bytes. Now 0F itself. This 0F over here, which corresponded to the NZB, now got consumed over here because it is one of the arguments that C7 expects. Right? C7 expects 5 bytes as arguments, so you consume the processor. If you start reading from here, 1, 2, 3, 4, 5 will consume those bytes. Okay, so now that is done. Now the processor starts reading from the next byte. What do you read? Well, you read 95. What's 95? 95 is the instruction exchange EBP EAX. Okay, you go look at the processor manual. That's what it is. And then that's just a 1 byte instruction. Then you read 45. What is that? 45 is increment EBP. Okay. Then you read C3. That's the ret instruction. So you see, how out of nothing, where there was no ret instruction sequence over here, we manufactured a ret by just choosing to read from an appropriate location. Okay. So you can always manufacture gadgets. That is the point, right? You need not have a ret instruction in your actual program. You can actually manufacture a ret even if it's not explicitly there as a ret, by just reading from C3 and interpreting bytes suitably. Okay, so that's the idea behind how you do a gadget search. And hey, that's the algorithm over here. You can read it in the paper. they search for gadgets in this particular way. But I'll just give you the high level idea. You can follow the instruction. You can follow the algorithm yourself. You go to C3, interpret that as a ret. Just follow a greedy algorithm. Okay, look for 45. 45 is EBP. Well, take that as an instruction sequence. Next, 95. Okay, that's the exchange. Put that as an instruction sequence, right? And the address at which this 95 byte. Remember, every one of these bytes in the program's address space has an address. There, after all, it's code that's sitting in the program's address space. This is address A. This is address A plus 1, A plus 2, A plus 3, A plus 4. Every one of these bytes is at a particular addressable location of the program. Okay, so all you have to do is to figure out where your gadget starts. You can choose to start your gadget at 07 if you want. I don't even know whether 07 corresponds to a valid instruction. If it does, well, you can go and look up the x86 manual. If it's a valid instruction, hey, that's the start of a gadget. Why not, right? But that's how you search for gadgets, right? And the idea is that, as I was mentioning to somebody who was just asking a question, if you have a gadget, let's say that this C7070000F 9545C3. This is a gadget because it's an instruction sequence that ends in ret. This is not a gadget. It is not a gadget because it does not end in ret. Okay. If you were to start interpreting this instruction sequence from F7, well, the C3 gets consumed as part of the second instruction in ZB, which is not a ret. So this is not a gadget. This is a gadget. Okay. So you start reading from C7. That's a gadget. Now, what is a gadget? Well, any valid suffix that's also a valid instruction sequence is a gadget. So the minute you start reading from C7, the next 5 bytes are consumed by this guy. Okay, but if you read from 95, that's a gadget. 9545C3, that's a gadget because exchange increment return. 45C3, that's a gadget. Okay, so any let me just put this in quote unquote. Any valid instruction sequence of a gadget is also a gadget. Okay. Any valid instruction sequence of a gadget, any valid suffix instruction sequence of a gadget is also a gadget. Okay, so if you've got this property where you want to store these gadgets as strings, okay, C700, this is a gadget. Now the next valid gadget is 9545C3. It's actually a suffix of this. This guy is another suffix of this. Here is an interview question that you might expect in your placement, right? It's a simple data structure question. If you want an efficient data structure to store suffixes or a suffix tree, what is that called? Time to start preparing for your interviews. You're in year 1, but doesn't matter. What is a suffix tree called? There's a specific name for it. Somebody's any answers? It's actually called a trie. Okay, a trie is a suffix tree or a prefix tree. It's an efficient data structure to store suffixes of strings, right? So over here, not all suffixes of the string starting with C7 are gadgets, but there are valid instruction sequences over here that are gadgets. So this is a gadget. You have a gadget starting at 95, gadget starting at 45, gadget C3. So you can store all of these gadgets compactly in this data structure called a trie, and that's exactly what this algorithm Galileo does. So if you go read the paper, you will actually see the Galileo algorithm in a fair bit of detail, but I've given you the high level idea of how you search for gadgets. Well, you start at C3 and then start searching using a greedy algorithm to go and find more and more of these instruction sequences that form a gadget, and just build up your suffix tree that way, right? You build a suffix and then you add more stuff to it. You build a longer string. So in the end, you end up storing a set of strings and their suffixes. They are valid suffixes, if you will. And the efficient way of storing this is as a trie. So, supposing I give you a body of code such as the standard C library or the math library or something like that, you can actually run this algorithm Galileo on top of it and harvest a database of valid gadgets that you can find from this library. So the way that you would index this database is that you would go and store all of the gadgets, and then you would also tell me the address at which that gadget starts. So that if that library I know were loaded to the program's address space, me as an attacker, I know exactly what the gadgets are and I exactly know which addresses they start at, so that I can override the return address of a vulnerable program in a suitable way to now string together gadgets to form my exploit sequence. Okay, so that's the gadget search algorithm. Of course, you should go and read this, but here are some answers, right? So why a try? Not any suffix, but any valid suffix, quote unquote valid. As I told you, what is a valid instruction sequence? I just told you of a gadget is also a gadget, right? So why start searching for C3? Well, it's easier to search backwards, right? If you find a ret, you can find sort of valid instruction sequences and go on. And they have some optimization criteria in the paper as well. They sort of look at boring instruction sequences and remove it. Well, this is what I said. If you read a textbook, you would never find the word boring because nobody would buy that textbook. But hey, this is a research paper, right? I mean, the author needed a name to refer to some instruction sequences. He just chose the name boring and he found it and he sort of used it, right? So what's a boring instruction sequence? Well, it's an instruction sequence that forms a gadget, but not really an interesting gadget. That's why it's boring, right? So if you find a leave instruction followed by a ret instruction, hey, that's boring. I really don't want to put that in my database. I'm going to find thousands of such gadgets anyway. So there are a few such other instruction sequences that are common that he doesn't really want to sort of put this database. So you search for gadgets and then you throw away these really common gadgets that you can anyway find with the program's address space. So the Galileo algorithm actually sort of discards these kind of non-interesting gadgets also that are gadgets according to the definition, but are not really interesting from the perspective of exploit development. Okay, so now let me actually move to the example of gadgets and then show you how you can load stuff from memory. Okay, so here's the deal. Okay, what I'm going to be showing you, and I will just show you 2 or 3 examples and then let you read in the paper at home. So what I'm showing you over here are how the stack would be laid out when you are creating an exploit. And what you see over here, these arrows over here just mean that this particular location on the stack is going to be overwritten with the address of this gadget. So you see over here a gadget, pop edx followed by ret. This is a gadget like G1 or something like that. G1 is sitting at address A1, and what this dot over here corresponds to is A1. This you would override these 4 bytes with A1 that point to this location over here, pop edx and ret, and this is a gadget that's sitting somewhere in the program's address space. So let us say that you want to now create an exploit, and as part of this exploit, one of the steps involves writing a particular constant into this register edx. Okay, and what is that constant? Well, I just chose a constant over here. It's called dead beef. I'm sorry if I sort of offend your sensibilities over here, but this is a very common name that is used in the hacker community. You will notice that they are all just hexadecimal values, and so that's why it's written over here. But anyway, you want to load this hexadecimal value into this register edx. The way you would go about doing it is by configuring your stack like this. In other words, you would create your exploit and overwrite the stack in the following way, right? This is the top of the stack. You would go and overwrite the return address to actually point to this address of this particular gadget pop edx. So if this gadget is called G1 and the address where it's stored is A1, you would write A1 over here, and then the next 4 bytes of the stack are not, you would just overwrite them with the value DEADBEEF. Okay. So now just imagine what happens when the program returns. When the program returns, it's going to think that this is the return address and start executing this stuff over here. What is this guy doing? Well, it's a pop instruction, pop edx. Pop edx means that it's going to read the next 4 bytes from the stack. That's what the pop instruction for edx does. It pops the next 4 bytes from the stack and it stores that value in edx. Okay, so the processor will just go and pop the 4 bytes corresponding to DEADBEF, copy it to edx, and the next instruction that it will execute is the ret instruction. So the next gadget in your attack sequence that you want to string together that you will put over here will be put over here just above this dead beef over here. So you will put that over there, and then that will then now execute the next instruction sequence in your attack sequence. So here is another example that shows a slightly more complex example. it is from the paper itself. As you can see, it's figure 3 in the paper. Load a word in memory to EAX. Okay, so so supposing that you want to load a word from memory. Right now, you are actually saying, okay, you're simulating the equivalent of EAX equal to star of P, where P is an address that is in memory that's storing some value, and you want to load it. Okay, so here is how you would do it. What I'm showing you on the right over here are two gadgets that just happen to be in the program's address space. Now you might ask me, hey, why movl64 EAX, EAX and followed by ret? This is not something that I created or the author created. It's just a gadget that he found in the program's address space. Likewise, pop EAX and ret. It's a gadget that's already there in the program's address space. We have to take gadgets that are there and put them to use. Okay, and using these gadgets, I'm going to implement functionality that I want. Okay, so how do I do that? Well, so I want to load a word in memory to EAX, and let's just say that the word that's there in memory is at this particular address. It just happens to contain the value deadbeef, it need not. But this is the particular word in memory that I want to read, and I want to store it to the register EAX. Okay, so how do I do it? Well, it just so happens that I have these particular gadgets with me to play with. What I would do is the following, right? The first thing that I would insert over here is the address of this gadget, pop EAX followed by ret. The next thing that I would put over here in the next byte on the stack is that I would put the address over here, so that if I add 64 to that address, I get the address of the memory location that I want. In other words, supposing the particular memory location that I want to read from is, let's say, I'm going to call that X, I will put the value X minus 64 over here. Why X minus 64? Well, the reason I want to do that is because, well, the next instruction is this particular instruction over here, move L64 EAX to EAX. Okay, now let's see how it works. So the attack starts. I'm going to read this first address. It's going to execute this thing over here, pop EAX ret. So what does the pop do? Well, it pops the next 4 bytes, which is this X that I stored over here, and it will store it EAX. The next guy, what does it do? Well, it's saying take EAX, add 64 to it, okay, and dereference that memory location. That's what this instruction over here is saying. Take EAX, which is X, add 64 to it. What do you get when you add 64 to X? Well, you get this address, dereference it. So you read this value over here and store it in EAX and ret, and so on. Okay, so what you saw over here is just one particular step in the attack and how I implemented it. A long attack will obviously have a sequence of such steps, and you have to string them together suitably. Okay, so what I will do is let me just start from here. Next class, I will show you. So I showed you how to load a word to memory. Next class, I'll show you how to store a word to memory, how to implement addition, and how to implement conditional jumps and so on. So all I will request you before you come to the next class is to read the paper. Right, the paper actually contains how it shows you how to create a Turing complete programming language with these gadgets. So work out the gadgets step by step. It will make the discussion much easier as I'm explaining. These are not easy things to explain, but they will sort of sit better in your head if you have read it once and I explain it, and you can relate to what you have read in the paper. So I will start from storing from memory, slide 81 or so, and I will sort of explain to you how these gadgets work. But that's return-oriented programming. I hope you got the main ideas. The next class, at least the beginning of the class, is going to be some more details of how these gadgets are strung together. And I will explain 2 more exploits. As I said, heap-based exploits, format-free exploits, I mentioned them. But unfortunately, we are out of time. Of course, next class is always there to explain them. So I will explain them in the next class. I have time for probably one more question. I see Gokulnath's hand is raised. Please go ahead, Gokulnath.
Sir, is there any way we can make infrastructure ISAs robust to these kind of attacks? For example, would this work on newer ones like RISC-V or something like that, sir?
Excellent question. Excellent question. So that was a question that these authors also had, and 2 years down the line, they also showed how to implement return-oriented programming on the Spark. So you might not have heard about Spark, but Spark was Sun Microsystems instruction set, which is actually a RISC architecture. Okay, so they showed that it's possible to implement return-oriented programming or RISC architectures also. So short answer, I do not know whether RISC-V in particular would be vulnerable. It's a very good sort of research project that you can do, but I would point you to the in fact, go Google the name of this particular author. He's Hovav Shaka, and go see his 2010 paper where he showed how to implement, or 2008 paper, sorry, where he showed how to implement return-oriented programming using RISC, and then you can see those ideas extend to RISC-V. I don't see why not, but it's certainly possible. Excellent question. Shaukat, you have a question?
Yes, sir. For this kind of attack with the gadget, as an attacker, am I to assume that the load addresses for the text program text is same, like it's consistent across all the machines? Because otherwise we would not know the gadget address.
Question, right? So what you're saying is, like, how do I know that the address are deterministic? And yeah, it's not always deterministic, especially if you've got address space layout randomization. But as I said, we are showing a proof of concept. So we'll make life easy for ourselves as an attacker and show a proof of concept. Now, there are ways and means by which to defeat address space layout randomization also. If you had address space layout randomization and you had stack guard, and all of these other defenses, it just makes the job harder for the attacker. Not impossible, harder, because now your attack is not just going to have to be the exploit sequence, but also the techniques that you use to bypass these things. And often, these attacks you find are not single stage attacks. The attacker uses a multi-stage attack. So for example, one way to defeat address space layout randomization. So what is address space layout randomization? I haven't explained it, but let me just briefly mention it. It is a defense technique where you introduce randomness into the program's address space by, for example, by changing the base address of the stack, okay, or changing the offset at which code is loaded, or so on, right? But the point is that once this randomness has been introduced to the program's address space, the randomness does not change until you start the program for the next time. Okay, so one way to defeat this is to actually leak the value of a pointer. Okay, if you leak the value of a pointer, which is, for example, if you can read the value of a pointer using a first stage exploit, you read the value of a pointer and then you read it in a program that's not executing address space randomization. If you subtract it, you know exactly what random value you used, and then you just add that random value to your exploit. Okay, and it will work on that particular instance of the program. It will not work if you restart the program, but it will work on that particular instance of the program. So these are called pointer leaks. This is how you would defeat ASLR, and it just makes the life harder for the attacker. Last question, please, Aman.
Hello, sir. Am I audible?
Yes, you are.
Yes, sir. You showed a slide where a particular hexadecimal instruction encoding was there. It means the same encoding had two different interpretations. Can we go to that?
Yeah, I'll show that slide. Yeah, here, this one. Yes.
Sir, the algorithm says that you have to read the instruction sequence from C3, right?
Yes.
And you showed that, like, if we read from starting, there are two different interpretations.
Yes.
Oh, okay. Actually, I thought, like, if we start from starting there are two different interpretations, and if we want the one which we actually ignored, but if we start from starting, there will be no red.
No.
Actually, I got confused.
I made it a point to emphasize that the first one is not a gadget. It is not a gadget because it does not end in a red, right?
Okay.
You start from C3. See, the point of showing you that was that gadgets exist in the most unexpected places. Even if you don't have a red statement, it can be used to create a gadget. That's what I showed. The first one is not a gadget. The second one is a gadget if you read from C3 backwards, right? Okay. That was the point of showing this. It was not to illustrate that the first one is a gadget and the second one is a gadget. The first one is not a gadget because not ending with a red.
Okay. Yeah.
You can use it to manufacture a gadget because it's ending in C3. That's what I meant.
Okay.
Clear?
Yeah, sure.
Okay. So we will have to pause now. We are out of time. You can always ask questions in the next class, and of course, please read the paper. I cannot emphasize the need to read the paper beforehand, right? I mean, the reading is not optional; it's anyway required for your exam and so on. But if you read it before the class, you will probably follow the class much better. Okay. So with that, let us stop for today. All right. Thank you very much.